what does all of this have to do with spans and projections, you may ask? Well, let's reframe what we were talking about before we introduced matrices. The idea was to find the vector in the span of x1 and x2 that is closest to y. Okay? And vectors in the span of x1 and x2 look like w1 x1 plus w2 x2. So I'm saying, of all the things I can write in this form, which of them is closest to y? Okay? That is, which of them has the smallest error vector? The error being y minus my linear combination of x1 and x2. And the answer we agreed upon is that the linear combination that we are looking for is the one whose weights, w1 and w2, satisfy x1 being orthogonal to the error vector and x2 being orthogonal to the error vector. Okay? That's what we concluded before. If we want w1x1 plus w2x2 to be as close to y as possible, well then we need to choose w1 and w2 so that the resulting error, this piece in here, is orthogonal to x1 and orthogonal to x2. That was our conclusion of the discussion before we got to matrices and vectors. Sound okay? All right. And where we left off was the fact that this is just a little complicated to try and solve on its own. Okay, so what can we do to make that easier? Well, let's use our understanding of matrix vector products to try and not have to keep track of lots of separate equations. Okay? Remember, I told you to think of a matrix as being the result of taking several column vectors and putting them next to each other. And so let's do that here. Instead of having to keep track of two separate vectors, x1 and x2, let's just stack them next to each other into a single vector, x. Okay? And so, or sorry, not a single vector x, a single matrix x. Okay? What's in the matrix x? Well, it's just the numbers in x1 in the first column and the numbers in x2 in the second column. So it might look something like 2, 5, and 3, -1, 0, and 4. Okay, so when I refer to the matrix x, I'm talking about this thing. Okay? Now, where does the linear combination come into play? Well, the idea is that before, I had to keep writing w1 x1 plus w2 x2. And remember, here I only have two vectors that are spanning the space I want to project onto, x1 and x2. But what if I had a third x, or a fourth x, or 70 x's? I don't want to have to keep writing this 70 times, right? And so the idea is to rewrite this linear combination using matrix vector multiplication. And the way I will do it is by defining a new vector, w, who has two components in it, w1 and w2. So w is a vector, but w1 and w2 are scalars. And what this allows me to do is multiply x by w. And when I do that, that gives me w1 times the first column of x plus w2 times the second column of x. Right, this is the same as what we did here. Right, it's the first element in the vector times the first column plus second element in the vector times the second column. It's exactly the same thing. Right? So it looks like w1 times 2, 5, and 3 plus w2 times -1, 0, and 4. And this is the same thing as this linear combination that I've been manually writing out every time. And so what's the point of all of this? Like, what is the one reason I put the slide on the lecture? it's to emphasize the fact that instead of writing w1x1 plus w2x2 plus w3x3, I can just write matrix x times vector w, where the matrix x comes from taking all of my individual x vectors and putting them next to each other in one big matrix. Okay, that's how I constructed the matrix x, and I can represent linear combinations of this matrix x just by matrix x times vector w. Because as we saw, one way of thinking of matrix vector multiplication is as being a linear combination of the columns of x. But the columns of x here are just the two spanning vectors I had before. Okay, so any vector in the span of x1 and x2 can be written in the form x times w. Change the numbers in w, well then you're changing the weights on x1 and x2. That's the big idea. Linear combinations of x1 and x2 are just of the form matrix x times vector w. Okay, what questions do we have with why we can express this linear combination as this matrix vector multiplication? Okay. Now, what can we do with that? Well, one benefit is that instead of having to write my error vector as y minus w1x1 minus w2x2, there's an easier way of writing that. Right? Before, here I had to say w1x1 plus w2x2. But now I can just write matrix x times vector w. So that's one tangible benefit, and my goal is to find the vector w that makes the length of this error vector as short as possible. Right? Note that here the only unknown is the vector w, that is w1 and w2. Y, I know what it is. I have an example here. And the matrix x, I know what it is too. The only unknown here is figure out the w that makes the length of y minus xw as small as possible. That's it. Okay? And before we started looking at matrices and vectors, we left off with this statement of the problem. That is, the w1 and w2 that make the error vector as short as possible are the w1 and w2 that satisfy these two equations. But it turns out I can rewrite these two equations much simpler using the fact that this linear combination piece is really just x times w. So what I want to do is simplify this system of equations as much as I can into a way that I can easily solve it. That's the concrete goal of the rest of today's class. Make it so that I can actually find w1 and w2 here. Because the way it's written right now, it's not clear how I would do that. And so how am I going to simplify it? Well, first I'll start with the fact that instead of, again, having to write w1x1 plus w2x2 all the time, I can just write xw. What this means is that I can rewrite the error vector, which previously I was writing as y minus w1x1 minus w2x2. I can write it as just y minus xw, which means that in here, this is just y minus xw, and this is just y minus xw. So this system of two equations and two unknowns can be written as x1 dot producted with y minus xw is 0, and x2 dot producted with y minus xw equals 0. Okay? So that was one simplification. My goal is to find the vector w that makes these two things hold true. That's still what I'm searching for. But this yet doesn't really seem much simpler than what I already had. But it turns out that using our understanding of matrix vector multiplication, I can condense these two equations into just one big equation. And what's that big equation? Well, let's find out. Okay. Let's not box this just yet. Okay. So, again, my goal is to combine these into a single equation. And notice what I have here are two dot products with the error vector. It's x1 dot product error vector is 0, and x2 dot product error vector is 0. Okay? And so to figure out how to combine these into a single equation, let's go back to our matrix X, which in this case is 2, 5, 3, negative 1, 0, 4. Remember, I constructed this by taking my x1 and x2 vectors and stacking them next to each other. Notice what I have over here are the dot products of these columns with the error vector. Right? It's first column dot product error vector is 0. Second column of x dot product error vector is 0. Okay? Now, think back to when I introduced matrix vector multiplication. One interpretation is that it creates a linear combination of your columns. And we already use that, right? We're using W1 and W2 as being weights on the columns of X. But what about that other interpretation? As being a sequence of dot products with the rows of our matrix. This is similar to what we were doing on our current slide. But what I have here are dot products not with the rows of X, but with the columns of X. Right? But how do I change the rows of X, or the columns of X, into the rows of something else? You take the transpose. Right? So what would happen there? What if I take the transpose of X? Well then, instead of having 3 rows and 2 columns, it's now going to have 2 rows and 3 columns. And it's going to result from taking the transpose of the first X vector and the transpose of the second X vector. Numerically, here it'll look like 2, 5, 3, negative 1, 0, 4. Okay? What do I do with this? Well, now pretend I had my error vector just written over here. The numbers in it don't matter. If I took the product of X transpose with the error vector, what would it end up doing? Well, it would take the dot product of the first row of X transpose with the error vector, and then the dot product of the second row of X transpose with the error vector. But the rows of X transpose, how are they related to X? They're the columns of X. Right? The rows of X transpose are the columns of X. Right? Rows of X transpose are the columns of X. What does that mean? It means that I can rewrite these two equations as this. X transpose y minus xw equals 0. Okay? What this is doing is multiplying, or it's taking the dot product of every row of this thing with the error vector. Right? Because that's one of the views of matrix vector multiplication we saw. Right? A times V, what does that do? It dot products V with every row in A. So here, this is dot producting the error vector with every row in X transpose. But the rows in X transpose are just the columns of X. And so, this is a concise way of stating the two equations above. Okay? And just to really make it clear, if I work out what X transpose E looks like, it'll be like, the first X vector transposed the second x vector transposed times e. But when I do this multiplication, it's going to take my errors and dot product it with x1, and then take my errors and dot product it with x2. The result will look like this. x1 transpose e and x2 transpose e. Remember, the dot product of two vectors can also be written as the first vector transpose the other. So that's really what's going on here, right? This is the dot product of x1 with e, and this is the dot product of x2 with e. So it's really just combining x1.e and x2.e into this vector. Okay? And so maybe I can color that with, this comes here, and this came here. And I want that to be 0. Okay? And so, taking a step back, what does this all really mean? Well, what we established is that the W1 and W2 that make my projection error, y minus xw, the smallest, are the W1 and W2 that make it so that x transpose error equals 0. Okay, that's what we saw in the previous slide. But then we know our error vector is just y minus xw. I've put a star on it here because it's the one satisfying this like optimal set of criteria. That's what was on the previous slide. And we might want to solve and isolate for just a formula for W star. And to do that, I can start by expanding out or distributing this set of parentheses here. Okay, and write this as x transpose y minus x transpose x W star, and that's 0. And in my mission to solve for W star, I can add this term to both sides, and that gives me the W whose components minimize projection error is the W such that x transpose xw equals x transpose y. Okay? Now, if I want to isolate for W here, what would I have to do? I'd have to try and get rid of x transpose x. And how can I do that? Well, I can multiply on the left by x transpose x inverse, because that'll allow me to cancel out the x transpose x. But that'll bring an x transpose x inverse over here as well. Okay, and I'll show you that on the next slide. But just to take a step back, what I've highlighted here is called the normal equations, plural. Even though it only looks like one equation to us, like there's only one equal sign. Why is it called the normal equations? Why is it plural? What's plural about it, even though there's only one equal sign? Yeah?
Because they are matrix and matrix are a system of linear.
Yeah, it's because what's highlighted here really represents a system of linear equations, all of which must satisfy this criteria. It's like kind of related to the fact that here there were multiple equations that I condensed into just a single one. Why are they called normal? It doesn't mean normal in terms of regular, but what does it mean? Orthogonal, yeah. Normal is just another word for orthogonal. Okay? Now, if we try and solve for W star, it requires, as I showed, multiplying on the left by the inverse of x transpose x. But that can only be done if x transpose x is invertible, which it isn't always. Okay? And this is something we will explore a bit more in the coming lectures. But just so it's clear what the purpose of all of this was, we started off today by saying, or asking, of all the vectors in the span of x1 and x2, which of them is closest to y? Well, we know the answer. The answer is that it's the vector x times w star, where w star, if we can compute it, is this, x transpose x inverse x transpose y. Now that's an abstract concept, but just to illustrate, for our matrix x and vector y, I just plugged it in to NumPy and figured out what x transpose x inverse x transpose y was. And it gave me these results, 0.7289 and 1.6300. So concretely, what does this all mean? Like, what was the purpose of today's lecture? It was to find these numbers. Like, how do I know what to multiply x1 by, and how do I know what to multiply x2 by? Well, I do x transpose x inverse x transpose y. And there are a ton of assumptions baked into where this calculation comes from, but concretely, that's what it boils down to. It told me what to multiply x1 by and what to multiply x2 by, such that the resulting vector is the closest vector to y possible. Okay? So when we come back next class, we will revisit some of these ideas and then see how they are related to regression.